Good day. We are the proponents of the study entitled Development of a Prototype Arduino-based Water Level Warning System for Early Flood Detection in Binangbang River. I am Matthew D. Manalo.
I'm Kimberly Claire V. Bradel.
I am Harvey Encarnacion.
I am Maria Elizabeth M. Igaya.
And I'm Christine Ida Ramos.
For at least 18 years, Barangay Navotas has sheltered us. Oftentimes, we experience flooding because of the Binangbang River. During strong typhoons like Odette, the river overflows, bringing flash floods on the land. But despite these overflowing instances, there is no water level monitoring system that monitors the river. This makes people unaware of when will the river overflow. According to ADRC, an average of 20 typhoons visit the Philippines every year. NOAA's maps show that the Binambang River and its nearby barangays are susceptible to flooding. One study states that predicting flood by monitoring the river's water level is a good mitigating strategy because rivers are common causes of flood. Several researches were conducted to create water level warning systems. Some of these are the study of Akbar, Masafa, and Rianto that developed a system with a programmed webcam as the water level sensor. On the other hand, Shatpatananon et al. Used a capacitive sensor that takes advantage of the capacitance of water to determine its level. And there is the study of Juan Hassan and his team that utilized float switch sensors. However, the sensors have their limitations. The webcam, for example, may get inaccurate results if its lens is blocked or if there is low light. Meanwhile, the capacitive sensor and the float switch sensors need to be in contact with the water to operate. This makes them prone to damage caused by the river, especially if the water current is strong. But ultrasonic proximity sensors provide solutions to this. This sensor is a contactless distance measuring device and it uses ultrasonic sound waves to determine the water level. HCS004, an example of the sensor, works by getting the time interval between its generation and the reception of ultrasonic waves. To get the water level, we use the formula water level equals reference height minus speed of sound times time over 2, where the reference height is the distance between the sensor and the reference point or line, while the speed of sound times time is derived from the distance formula. But speed of sound is not constant all the time. Studies show that temperature and relative humidity have direct effects to it. It is described by the equation being presented, and combining the equations will result to this formula. Though, aside from these quantities, there are other factors that affect the readings of ultrasonic proximity sensors, like the air density, the sound-absorbing property of the object being detected, and the angle between the sensor and the object. Hence, these are the limitations of this study. Having said this, we developed a prototype of an Arduino-based water level warning system that can monitor the water level of the Binambang River and detect early floods. HCSR04 is the water level measuring sensor, while the DHT11 sensor is used to determine the speed of sound for more accurate results. For the warning devices, LED lights and a buzzer are used as warning indicators. Also, an LCD panel is used to display the process data. All of these components are controlled by an Arduino Uno microcontroller.
Throughout our study, we aim to develop a water level warning system and evaluate its performance. Specifically, our study intended to answer the questions. What is the absolute error of the water level computed by the water level warning system? This will tell the accuracy of the system. Is there a significant difference between the actual water level and the computed water level? To give more context, the actual water level is the water level that the researchers manually measured, while the computed water level is the water level that is computed by the system with the help of the sensors. What is the response time of the water level indicators, which are the LCD panel, LEDs, and a buzzer? This will tell how long it takes before the water level indicators indicate the water level. Is there a significant difference between the response time of the water level indicators and their acceptable response times? This will determine whether the response times of each water level indicators is acceptable. In here, we use the acceptable response times that Cabot et al. Used in their study. Conducting this study will benefit the following: the residents of nearby barangays. By using this warning system, signals can be sent to the residents about the current status of the Binambang River. These signals can help them to prepare for the potential flooding that may occur. The local government. Using the data that this system can provide, the local government can try mitigation and even flood control strategies to reduce the possible impacts of flood caused by the river. People living near water bodies that are susceptible to flooding. This can help them to create their own warning system that will monitor the status of a water body, for them to be warned about the potential flooding that may occur in their area. And lastly, for the future researchers, this study can make their basis to create a more accurate and improved water level warning system.
To conduct this study, we constructed an experimental setup that we use to gather all the data that we need. The setup has two main parts. The first is the data gathering tool comprising the Arduino based water level warning system and a measuring stick, while the second part is the water barrel filled with water that represents the river. Actually, our initial plan was to gather data at the Binombong River, though the water level during that day was low. And since the side of the river was steep, we found that it might be dangerous if we still choose to gather data there. So we decided to just use a water barrel. In constructing the setup, we first gathered our materials. We bought most of them in Lazada and Shopee. This include the Arduino Uno, the sensors, and the water level indicators. Meanwhile, some materials, like the water barrel and the measuring stick, were already available in our respective houses. Afterwards, the plywood was cut with dimensions 30 centimeters by 17 centimeters. Next, we nailed the measuring stick to the plywood. This measuring stick was made from a 1.5-meter bamboo stick that was labeled with 0 to 100 centimeter to measure the actual height of the water. The 100 centimeter is what we used as the reference height for the formula earlier, and 0 centimeter is the reference point. We divided these heights into categories, namely the normal, above normal, high, critical, and overflowing levels. This table presents the level categories in which these relative heights are divided. After nailing the stick to the plywood, we glued the electronic components into the plywood to form the system. Then we programmed the Arduino board using a laptop. The picture being presented shows the flowchart of the program. This tells that when the system initializes, the Arduino Uno sends signals to the sensors to read the water levels, the temperature, and the relative humidity. Then it sends signals to the LED panel to display this data. Simultaneously, the Arduino processes this information and decides whether it will turn on the warning indicators depending on the water level. Example, when the computed water level by the system is 50 centimeters, which is considered as high, then the Arduino will turn on the LEDs 1, 2, and 3, and it will tell the buzzer to generate the alarm 1 sound. But before we actually use it for gathering the data, we tried the system first by placing our hands on the sensors to check whether the system will function correctly.
For the data collection procedure, we first fill the water bottle up to its maximum capacity. After that, we place the data gathering tool above it to start the gathering process. For SOPs 1 and 2, we conducted 10 trials as shown by the table. We performed this by submerging a specific length of the stick in the water. For example, in trial 2, we aim to collect the computed water level by the system if the actual water level is 10 cm. So we submerged 10 cm of the stick, then we looked at the LCD panel to get this computed water level. For SOPs 3 and 4, we measured the time interval before the water level indicators turned on to indicate the water level. We placed first the data gathering tool directly above the water surface. Then we placed the paper under the sensor at a specific height to turn on the indicators. The time span before the indicators respond to this change in water level is the response time. To measure it, we took a slow motion video of this process. The table shows the trials that we conducted. As you can see, there are only 4 trials for the LEDs and 3 trials for the buzzer. That is because the green LED that indicates the normal water level is always turned on. We made it this way because anything below the above normal level is considered normal water level. Also, this LED doubles as an indicator that the system is turned on and is functioning. On the other hand, the battery has only 3 trials because we program it to alarm just when the water reaches high, critical, and overflowing levels. A video clip that we used to get the response time is seen on the screen.
To analyze the data, we used Microsoft Excel and IBM SPSS software. For SLP1, we used absolute error and mean absolute error formulas to identify the measurement error of the system. For SLP2, we used independent samples t-test to determine if this measurement error of the system is significant. Meanwhile, mean formula was used in SLP3 to compute the average response times of the water level indicators. And in SLP4, we used one sample t-test to determine whether these response times are acceptable. Hence, we obtained the following results. This table answers our first research question. It shows that the mean absolute error of our prototype Arduino-based water level warning system is 0.79 centimeter, meaning the computed water level by this system deviates by 0.79 centimeter on average from the actual height of the water. However, it is important to note that these results may also be due to the measurement errors that we have unavoidably committed. For example, when we were testing the functionality of this system, the computed water level that this system displayed was in the range of 0.38 centimeter to 0.42 centimeter. But it should be 0 centimeter because that is the actual water level that we have manually measured. Unfortunately, we could not solve this problem no matter what we did. Aside from this, other factors like air density and the angle between the sensor and the water surface may have affected the accuracy of the system as well. This is in accordance with the study of Bhatia and Patak.
Next, after performing the independent samples t-test on the dataset in SOP1, we learned that there is no significant difference between the computed water level by the system and the actual water level that we manually measured. This is supported by the value of P being greater than 0.05. This suggests the acceptance of the null hypothesis, which states that there is no significant difference between these levels. Therefore, we concluded that the computed and the actual water levels are almost equal to each other, and the deviations shown in SOP1 are insignificant.
Meanwhile, for the results of SOP3, this table shows the response times of each water level indicators. The first table in this slide reveals that on average, it takes 0.65 for LCD panels to display the computed height of the water. On the other hand, the next table tells that it takes 0.22 seconds on average for the LEDs illuminate to signify the current water level, while it takes 0.28 seconds on average for the buzzer play the alarm to tell the status of the water.
And we used these response times to get the answers for the SOP4. The results show that there is a significant difference between the response times of the LCD panel and the acceptable response time. This is due to the p-value being less than 0.05, and it is even below 0.001, which suggests a very high significance. Hence, we reject the null hypothesis, which says that there is no significant difference between these times. This just means that the LCD panels displays the reading of the water level in a quick manner, and the time it takes to display the data is shorter than the acceptable response time, which is 2 seconds.
Similarly, there is a highly significant difference between the response time of the LEDs and the acceptable response time. This is because the p-value, which is also less than 0.5, suggesting the rejection of the null hypothesis. So we can also say that the LEDs quickly illuminate to tell the water level. Also, the response times are much shorter than the 2-second acceptable response time. And for the buzzer, it is found as well that there is a highly significant difference between its actual and its acceptable response times. This is because of the computed p-value being less than 0.05, meaning the buzzer quickly plays the alarm whenever the water level rises to high, critical, and overflowing levels. Same with the other indicators. The response time of the buzzer is much shorter than the acceptable response time.
Using these findings, the following conclusion were drawn. On average, the computed water level by the prototype Arduino-based water level warning system deviates by 0.79 centimeter from the actual water level. But despite this deviation, the computed height of the water is still almost equal to the actual water height. We also concluded that it takes less than a second for the LCD panel, LEDs, and the buzzer to indicate the water level, and their response times are proven to be shorter than their acceptable response times. Thus, this justifies that the prototype Arduino-based water level warning system is accurate in terms of its measurements, and is also responsive in indicating the water level.
But to further improve the system, here are our recommendations. For better system performance, we suggest to use even more accurate and durable sensors like JSNSR040 or A02YYUW ultrasonic proximity sensor, as well as the SHT20 temperature and humidity sensor. We wanted to use these materials, but since they are more expensive, we could not buy them for this study.
Use an Arduino GSM module so that the system can send a text message to a local official's phone number so that he or she can update everyone about the current status of the Binambang River.
The use of solar panel is also suggested to power the water level warning system.
We also highly recommend to replace the LEDs with LED bulbs, and the buzzer with a siren or speaker so that the warning alerts could reach people even if they are far from where this system is located.
We also strongly suggest to enclose this system in a waterproof container since water may damage it. Lastly, place this Arduino-based water level warning system beside or under the Binambang Bridge.
But before we end this presentation, here's a short clip of how the developed system works. This is Group 6 from Fernando Guerrero, and we thank you for watching.